Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I want to make a relatively short video about theoretical problem, or I should say a problem related to theory, because the problem itself is not the problem herself is not a theoretical one at all. It's actually a very real problem that we have to beat our heads against, and that's connected to the input offset voltage of op-amps and what is the input voltage offset effect, or what effect does it has on instrumentation amplifiers. Because sometimes we want to use op-amps to basically create instrumentation amplifiers to make some more accurate differential measurements and so on and so forth. I'm not going to talk about instrumentation amplifiers themselves, because there are enough videos on YouTube and also articles on the internet that describe what an instrumentation amplifier is. I'm also not going to be discussing about differential amplifiers. Again, there are enough resources on the internet for you to learn. I'm making this video because I honestly haven't seen such a video made by others. I guess people kind of assume that once you understand the problem of input offset voltage, you automatically know how to apply it in all sorts of situations, which I think it's a bit of a wrong assumption. Up until recently, I didn't knew that I had this problem, so yeah, it's not a realistic assumption to make. Anyway, so I'm just gonna give you a brief overview. Like I said, there are plenty of other videos and articles that teach you exactly what the input offset voltage is, but as a brief overview, we know that an op-amp has two inputs. I'm gonna say a plus input and a minus input for the sake of simplicity, okay, because they are called inverting and non-inverting, but I find these names a bit hard both to pronounce and to understand, so I'm gonna just say plus and minus inputs. Now, ideally, an op-amp should see no difference between them. So basically, if we were to take the absolute simplest op-amp circuit, which is a buffer, and if we apply a certain voltage on the input, ideally we should see that voltage on the output as well, identical. So let's say in our example, if we apply a 2 volts DC voltage on the input, on the plus input of the op-amp, like I said, the op-amp is configured as a buffer, then we should theoretically have 2 volts on the output. However, we do not have 2 volts on the output because there's this difference in voltages that the op-amp sees. It's a byproduct of the fabrication process, and it's not something that you can that any manufacturer can remove completely. It's just something that they can do better, but it's this difference in voltages, it's gonna be present no matter what. So we can see this difference in voltages as an extra voltage in series with with our desired signal on one of the inputs. Okay, so in this case, let's say, for the sake of simplicity, that we have a 100 millivolt offset voltage. Of course, this is not a real example. In reality, the worst case input offset voltages are around a few millivolts, there's no way you can have a 100 millivolt input offset voltage, but we're giving this as an example for the sake of simplicity. Okay, so if we have a 100 millivolt and it's a positive voltage, and we apply a positive 2 volts on the input, on the plus input of the op-amp, then the op-amp will effectively see 2.1 volts on the input, and therefore will throw 2.1 volts on the output. If this voltage were to be negative, like this, then we would have a 1.9 volts, because 2 volts would subtract minus 0.1 volts, so the result would be 1.9 volts. Anyway, in both cases we would not have what we would want on the output, and so this is basically an undesired effect. Now, this is the general overview of what the input voltage, input offset voltage is, and yes, it's an input offset voltage, meaning it's an offset voltage that manifests herself at the input, not at the output. However, of course, it will have a big effect on an actual amplifier that has an amplification factor, because this input offset voltage will get translated into a much bigger output offset voltage, because it will get multiplied by the amplification factor of that particular circuit. And that is, of course, a problem. Now, we're not gonna discuss about that particular problem herself. We will be discussing in this video, and I will be showing you how is this problem affecting us in an instrumentation amplifier, because yeah, the general idea that I've seen on the internet is that this problem disappears on an instrumentation amplifier. However, that's not entirely true. It's just halfway true, okay, and it's true only in certain contexts. So for the sake of simplicity, let's just say that we have an instrumentation amplifier that does not apply any amplification factor whatsoever. So its sole point is to its sole purpose is to measure the difference in input voltages and recreate that differential voltage relative to the ground on the output. Okay, so if we have in an ideal case, if we have plus 1 volt and minus 1 volt input voltages, the difference is 2 volts, so on the output we should see 2 volts relative to the ground. Okay, for this our instrumentation amplifier has 2 buffers on the input, so they apply no amplification factor, and also all these other 4 resistors that are part of the differential amplifier on the right, they have perfectly equal value, so again, in turn, they do not apply any amplification factor. So ideally, we would have 2 volts, this difference on the output as well, relative to the ground. However, in reality, like I said, each amplifier is plagued by this input offset voltage. For the sake of simplicity, let's just say that it's 0.1 volts for all 3 of them. And it's positive 0.1 volts. Of course, this is not always true, but again, let's just take it for the sake of simplicity. Well, in this case, of course, each buffer will shift the input voltage a little bit. So at the output of the first buffer, instead of having plus 1 volts, we would have 1.1, okay, because it's 1 plus 0.1, and at the output of the second buffer, which sees the minus 0.1 volts voltage, instead of having minus 1, sorry, so the second buffer sees minus 1 volt on the input, so normally he should have minus 1 volt on the output. However, we will have minus 0.9 volts, because it's minus 1 plus 0.1 equals minus 0.9 volts. Now, it is true that at this point we don't really care all that much about this input offset voltage. Again, provided that both of these amplifiers have the exact same input offset voltage, both as a magnitude and as a sign. We don't have a positive and a negative one, both are either positive and or negative, because the difference between these 2 points will still be equal to the difference between the input points, right? If we make the difference between 1.1 and minus 0.9, we will still get 2 volts, just like on the input. So at this point, we don't really care that much. However, then this input offset voltage gets to screw our results a bit more than the usual. Now I've made some formulas, and I will explain the final ones, because we have 2 of them. Well, we have one of them, but if you consider the amplification factor equal to 1, then it simplifies to another one. But anyway, before that, let me explain to you how we can visualize this effect. So if we have here a 1.1 volt and here a minus 0.9 volt, let's just call these input positive and input negative. Then we have some intermediate voltages around here, and we can figure what's gonna be the output voltage of this differential amplifier. So on the positive side, we have a voltage divider. Again, let's consider that all 4 resistors have the exact same equal value. We have a voltage divider between this point of 1.1 volts in our example and the ground, which is of course 0, right? So exactly in the middle of these 2 resistors, we have exactly half of this voltage, so 0.55 volts, right? 1.1 divided by 2, 0.55. However, this is where the input offset voltage comes into play. We will consider that it affects the plus input of the op-amp instead of the minus. So the op-amp, instead of seeing 0.55 volts, he's gonna see 0.65, okay? Because we have 0.55 plus 0.1 equals 0.65. So that's what he's going to see on the plus input. Now, as we know, op-amps, in such a configuration, op-amps will attempt to do whatever possible with the output voltage so that they will keep both input voltages equal. So if we have 0.65 volts on the plus input, the op-amp will try to make it so that it will also have 0.65 volts on the minus input. But this particular point is at halfway across this other voltage divider here, which basically divides the voltage between the output voltage and this input negative voltage. So we know this point, this middle point, we know the negative side, and therefore the input side, and therefore we can do reverse calculations to figure the output voltage, which is the other side of this voltage divider. So on this particular resistor here, we have 0.65 minus 0.9, therefore 1.55 volts here on this resistor. If we have 1.55 volts here, then we must also have 1.55 here on this other resistor, because again, these 2 resistors have equal value. Therefore, the output voltage, because you know this other voltage is nothing else but the output voltage relative to this 0.65 volts point, then this output voltage is 1.55 volts. How much is on this particular resistor? Plus 0.65, which equals 2.2 volts. Okay, so we see that for a 2 volt differential voltage on the input and 0.1 volt input offset voltage on the output, instead of getting the same 2 volts, we get 2.2 volts. In other words, the input differential voltage plus twice the size of this input offset voltage. Okay, and if we are to calculate this for a different amplification factor, let's say that we have RF of different values and RE again different values than RF, so we have an amplification factor equal to the ratio between RF and RE. Then if we do, you know, mathematical calculations, we reach the conclusion that the output voltage will be the differential voltage, positive minus negative, okay, multiplied by this amplification factor, which is the ratio between RF and RE, plus the input offset voltage multiplied by the amplification factor plus 1. And this is significant because at high amplification factors, this error, because for us this amplified input offset voltage is an error essentially, right? This error becomes significant, especially when we want to have high amplification factors like 100 or even 1000. 1 millivolt of input offset voltage is enough to cause 1 volt in plus or in minus on the output. And yeah, at an amplification factor of 1000, that's certainly gonna be significant, especially since if we choose high amplification factors, it means that we have small voltages on the input, right? Small differential voltages, and therefore those input voltages will be basically comparable to this error voltage, to this input offset voltage, which is an error for us. So yeah, it's very easy for us to have wrong results in such a case. And this other formula derives from this one. If we make the amplification factor equal to 1, then we only have the differential voltage, right? Positive voltage minus negative voltage plus the input offset voltage times 2, because here we have 1 plus 1. So this is where this other simplified formula comes from, and it explains, you know, our 2.2 value in this particular example. Now let me also simulate it for you. I'm not going to show you anything practical because there will be future videos about that. So let me simulate this for you and you will see what I'm talking about. So let's say just a second to set up, because I've done other simulations before. Right, so we have here essentially the same circuit, the same plus 1 volt here, minus 1 volt here. So we have 2 volts of differential voltage on the input, a couple of buffers. We are taking a look at each buffer's output voltage, the positive one with blue, the negative one with red, and the final output with green. We have 10 kilo ohm resistors here, so all equal value, therefore no amplification factor overall. And we have here another voltage. It's a correction voltage, but for the moment we'll set it to 0, so it's exactly as if we ground this resistor directly. I have also set the input offset voltage of this op-amp to be equal to the VEO definition set here, so I can change it more easily. Don't ask me why, but I have to set it to 1 volt in order for the simulation to consider that I have 0.1 volts. whatever, let's just skip over this detail because I don't know why it doesn't really take that particular value, but it doesn't matter. So we have 0.1 minus, in this particular case, minus 0.1 volts of differential voltage for all of these three op-amps. So as a result, on the positive side, the buffer, instead of giving us plus 1 volt on the output, gives us 0.9, right? So 1 minus 0.1. On the negative side, instead of giving us minus 1 volt, it gives us minus 1.1 volts. Again, minus 1 minus 0.1 equals minus 1.1. I know that you don't see this very well because the numbers here are very small. Like, I could make them so they are a bit bigger, but they're still relatively small. But I'm gonna be, reading these values for you. Now, the difference between 0.9 and minus 1.1, it's still 2 volts. So again, it shouldn't bother us. It's just the opposite way relative to these examples where we had positive input offset voltage. Here we have negative input offset voltage. However, as we see, the output voltage, instead of being 2 volts, it's 1.8. Essentially, it's 0.1 times 2, less than the voltage that it should be, right? So here we had 2.2 volts, so 0.2 volts above. Here we have 1.8, which is 0.2 volts below what should be. Okay. Now, this clearly shows what I've shown you earlier. Also, in order to correct this problem, all we need to do is basically take this particular feedback resistor and make it so that it's not connected straight to ground, make it so that it's connected to the output offset voltage. In this case, the output offset voltage is minus 0.2 volts, so we need to have here plus 0.2 volts in order for the two voltages to basically cancel each other. And so here on the output we see we have 2 volts if we apply this correction. Okay, and the same thing happens for let me make it 0 again. The same thing happens if we have a certain amplification factor, let's say an amplification factor of 2, by changing these two resistors. So normally we should have 4 volts on the output because 2 volts on the input times multiplied by amplification factor of 2 equals 4 volts. However, we have 3.7 because out of these 4 volts, this error gets subtracted, which is 3 times bigger than the input offset voltage, right? So we have 3.7 volts. So now if we want to correct this, we need to add with positive sign this voltage as an offset here, this output voltage of 0.3 volts, and voila, now we have 4 volts on the output. Okay, so I admit that this is a more of an advanced level problem. It's not something that we will bother with you know, on a daily basis in our circuits, in our projects, but it's still a problem that we need to take care of when we are doing something like this, so we need to take care of it, right? It's not a problem that we can ignore, that we can just ignore, okay? So, yeah, I hope you have found this useful. Thanks a lot for watching, and don't forget to subscribe if you haven't already. I'm gonna be making some more videos related to op-amps, and then some more videos building some devices with you for myself, and I'm gonna show them to you as well. So yeah, stay tuned if you want to see more. Also, if you enjoy my work, please consider becoming a Patreon. The faster I can buy components and devices, the easier it will be for me to learn new things, build new things, And the faster I can come here on YouTube and teach you as well, so that you don't have to spend so much time and energy, as I am spending. So thanks a lot for watching this video, and I will see you soon in the next ones. Bye bye.